Ladies and gentlemen, class recording has started. So, as we previously discussed, today, if you haven't turned in your equilibrium stations, please make sure that gets turned in over to the box on the side. As far as today goes, we are going to take our discussion of two-dimensional forces one step further, and everything we've done so far has been equilibrium, but we're going to change that today. We're going to take something that's not in equilibrium, nothing new conceptually, just applying what we know to a different way. So first, calendar. If we zoom in here. Alright, so yesterday you did your static stations lab, equilibrium stations in two dimensions. Like I said, today's date, highlight yellow, make sure you get that turned in. I will try to get it graded in a more timely fashion, so I'm not holding on to things quite as long. Today, we are going to do Newton's second law in two dimensions. So sigma F equals m times a, but in two dimensions. I got a couple of extra problems from a different book. Then you have the problem set that I just gave you. Answers to that problem set are posted online, so you can check those out tonight as you're doing some problems there. Okay? Tomorrow we get into the inclined plane. So basically we're going to talk about take things to a ramp. Conceptually, like I said, nothing new there, but mathematically it's kind of challenging. So we'll deal with that tomorrow, introduce those topics tomorrow. Okay? Then you guys are off on Monday, because after this brutal 4-day week, coming off of exams, we probably need a long weekend. So then on Tuesday when we come back, we'll continue on with the inclined plane. Then block next week, we will continue on with the inclined plane and talk about coefficient of friction, so we'll explain that lab a little bit more as we go along. Then Friday of next week, we'll be on the inclined plane again, but this time we'll be sliding down the inclined plane, like sledding on a hill where you're speeding up and stuff like that. The following week, Monday, to wrap things up, and then test on Tuesday of the following week. Not next Tuesday, the following Tuesday. Okay. Good there? All right. Let's take a look at our first problem for today. Our first problem for today looks like this. Let's shrink this up a little bit. So it says, a student attaches a rope to a 20-kilogram box of books. He pulls with a force of 90 newtons at an angle of 30 degrees with the horizontal. The coefficient of friction between the box and the sidewalk is 0.5. Find the acceleration of the box. So apparently we're in a situation where this 20-kilogram box of books is too heavy to carry, but we don't have like a cart or a dolly or something to put on with wheels, so we just have to tie a string to it and pull it along the sidewalk. Right? Do with that what you will. So, first things first, attacking this problem, sorry, do we need a second to write it down? Yeah. I'll give you a second here just to write some things down if you choose to. If you don't choose to write the problem down, then sit quietly. My physical science class last period had an interesting discussion about Manti-Teo.
Can we continue?
I'm sure they did. I don't know what there is to discuss. I don't know what there is to discuss at this point. But she wasn't real.
Yeah.
And she died. But
You wanted a sob story.
but then got all famous.
Wait, who died?
A fake girlfriend.
Yeah, a fake person.
Wait, the person who was talking to died?
No, she was.
No one died.
They made up the story that he had a girlfriend.
Some guy made up a law.
That's nobody's really quite sure. And so the discussion is like, did he make her out?
He definitely did.
And he went along.
He said he would call it, and his dad said that they would go to Hawaii.
I know.
Yeah, they said they met, but now he says they didn't.
The coefficient is 0.5. Yep.
Yeah.
He made her out.
Okay. We need another second. I just want you to know, just related to recording class today, every week, like usually like once a week, some random person posts a comment on like one of my class recordings, and it's just like, this helped me so much. Like, this was awesome. Like, just randomly, I have
Is
no
it the
idea.
same person every time?
No, it's different people. Like, I don't know if it's people like did their college that are looking for stuff and they like type in whatever.
That's so funny.
Yeah, and I get these weird comments like, this was great, it helped me so much. Like, I wish you were my teacher. So just I swear, that's shown up before on multiple occasions.
Just like a
Consider yourselves, yeah, this is like my Manti-Teo girlfriend. I make up a fake login. Yeah, I comment on my own stuff from a different login.
But I don't know what this is.
It helps my teacher evaluations a lot.
Look, I have all the names.
Mr. H said he goes on teacher.com. Puts fake ones. I would never even figure it out. Teacher.com. Never. All right, so let's discuss. Okay. So, first things first. The way we do this problem does not change. So, first things first, what are we looking for? You're looking for acceleration. Now, here's the thing where we apply it a little differently than we've done before. Okay? Because we are in 2 dimensions, theoretically we could have acceleration in 2 ways. We could have acceleration up or down, or we could have acceleration side to side. Based on the picture and what's given to us in this problem, which way is this acceleration going to occur in this problem? Side to side. So in this case, instead of just acceleration, why don't we make it a little bit more specific, and let's make it acceleration along the x-axis. That is our unknown in this problem. All right, I'm going to take this down here. All right, lots of things that we know. What's one thing that we know in this problem? Okay, they gave us the mass of these books, right? The mass of these books is 20 kilograms. Okay, which we can then use to do that, right? But let's just do the stuff in the problem, okay? So what else did they give us? Okay, they gave us a force, right? It's the force that this kid is pulling on the box, so we would probably call that what? Applied force, right? So we'll call that F of A. And it tells us that F of A is 90 newtons, but it also tells us that it's acting at an angle of 30 degrees. So theta is going to be 30 degrees in this problem. Okay? And then one more thing that they told us, right? The coefficient of friction, right? So I'll go purple on that one. The coefficient of friction in this problem equal to 0.5. Or 0.5. All right. What we're looking for, what they gave us to work with, now, probably maybe a little bit more important than when we were doing problems just in 1 dimension, let's take a look at our free body diagram. So, first force that we can put on this free body diagram is what?
Applied force.
We can put applied force on, that's fine. Okay. So, applied force in this direction, right? And as we've already established, this applied force was 90 newtons, and it told us that this angle here was 30 degrees. Okay? Other forces that we can put on here. Okay?
Force of gravity.
Okay, so force of gravity, right? Force of gravity in this direction here, right? We know how to calculate the force of gravity, yes? Okay? So you plug that into your calculator and you find out that the force of gravity acting on this object is equal to 196.2 newtons. Okay? Good there? Those are the only 2 forces that they actually gave us in the problem. But based on what we know and what we can assume, there would be 2 other forces that are acting on this box of books, right? What's one that's probably going to be pretty obvious? Well, let's go with the purple first, right? If they gave us a coefficient of friction, that means there's probably what on this box of books? Friction, right? Friction acts how on objects? Negatively, opposite, right? So in this case here, friction is going to act in that direction. Do we know how much friction yet? No. They gave us a coefficient, but right, coefficients don't go on free body diagrams. forces go on free body diagrams. Right? And then one more force that we can put on here, right? Okay, there's going to be a normal force in this problem, right? There's going to be a force coming from the ground acting on the books in this direction. Can we immediately label it as 196.2?
No.
In this case, we can't, right? Because the next step in our free body diagram is going to be what? What are we going to have to do next before we do anything else? Let's find our components, right? This applied force is not on the horizontal axis of this problem. It's not on the vertical axis of this problem. That means it has components. It has a horizontal component like this. It has a vertical component like this. Because of the information they've given us in this problem, we can find those two components, right? Using our trig functions, we can figure out what's the two components of that applied force are. Anybody run that through their calculator yet? The vertical component is going to be 45 newtons. Okay, and then 77.9 newtons for the horizontal components. Good there. Okay. Can we assume that the frictional force is equal to 77.9 newtons? No. That would be the case if what was true about this box of books. How would it have to be moving? Constant velocity. But in this case it says find the acceleration. So will the applied force in the horizontal direction or the horizontal component of the applied force equal to the frictional force? It won't. But there is one force that we can figure out from this picture based on what we've got here, right? What force can we figure out now? Normal. We said that this box of books is going to be moving which way? Which axis is this box of books going to be moving on? Horizontal x-axis. Okay? But if that's the case, right, if we're moving along the x-axis or accelerating along the x-axis, what has to be true vertically? Is there any motion on the vertical axis? No. If there's no motion on the vertical axis, we're in equilibrium on the vertical axis. Not total equilibrium, but just equilibrium on the y-axis. Does that make sense? Okay. So, in order to find the normal force, right, we take a look at our vertical forces. How many vertical forces are there in this picture? Three. Right? You got gravity downward, you got this vertical component of the applied force upward, but also normal force upward. Right? Two forces up, one force down. What has to be the case when we add them all together? We got to get to 0, right? So to find the normal force here, the blue one, what are we going to do? You're going to subtract this from this, right? Because the total up of the 2 has to balance out the 1 downward. Good there? Okay. So, say we put it in the calculator. What do you get? $151.2?
Yeah.
Okay. I know, it's kind of hard to see, I'm sorry. That better, Chuck? Alright, so 151.2, and we said that's going to be our normal force. Everybody making the connection about where we're going to go next? We have one force on this drawing that we don't know, right? It's what? It's the kinetic friction force. But the problem gave us the coefficient of friction. The coefficient of friction, we know, is defined as, in this case, Bridget, because it's kinetic friction, right, instead of the Fs max. We'll go FKF because it's just kinetic friction, but that doesn't change really what it means. But that's over what? That's over F of n. Right? That's That's our definition of the coefficient of friction. Okay? Do we know the coefficient of friction? That was given to us in the problem. Do we know the force of friction? That's what we're trying to find out. But we just calculated what? We just calculated the normal force as 151.2. So now we can go in and we can calculate what the force of kinetic friction is. I think it's probably going to be like 76. 75.6. Okay. So we'll take that back up to our drawing now, and we'll label this as 75.6. All right. Good. Anything really new so far? Not really, right? But now here's where we kind of put it all together and get something new, right? All the problems we've done up until this point have been equilibrium, right? So the net force is equal to 0 on both axes. But that's not the case in this problem, right? We're looking for acceleration. If we want to calculate the acceleration of an object, we need to know a couple of things. What are some things that we would need to know in order to calculate the acceleration of an object? We could know its initial velocity and its final velocity and the time, right? Because the first relationship for acceleration that we came across, right, was delta v over delta t. Do we have any kind of velocity information in this problem? No. So that doesn't really seem like the direction that we want to go. But we do have another really important relationship that we've established that includes acceleration, right? Newton's second law, right? So Bridget, if we want to calculate the acceleration of an object, what two other things will we need to know? Mass and net force, right? We know that net force is equal to mass times acceleration. Right? That's Newton's second law. But more specifically to this problem, we've already established which way is this box going to be accelerating? Horizontally along the x-axis. So we specifically want the x-axis acceleration. If we want x-axis acceleration, what forces do you think we probably should focus on? Only x-axis forces. So the net force on the x-axis is equal to mass times the acceleration along the x-axis. Well, let's talk about that, right? So now, does everyone see where I got this equation from? Yes? Yeah. All right. So now we look at net force, right? Net force defined as the sum of all forces, right? Let's go back up to our picture. How many horizontal forces are there in this picture? There are 2 horizontal forces. There is this one right here, the component of the applied force, and there is this one here, the kinetic friction force. Marty, go ahead.
How come you would include the 90 units as a...
So first, that's why here, Amani, when we took it here, we're looking horizontal as the equivalent of being on the x-axis, right? So if we take a look at that picture, that's a good question, by the way. Why don't we include the 90? Okay, just so people listening. Is that 90 on the x-axis? It's not on either axis, right? And that's why we broke it up into its components. So we've sort of mentioned the idea that breaking this 90 Newton applied force into its component vectors, or its component forces, is pretty much the equivalent of taking this out of the picture and just leaving us with these 2 forces. Because this applied force is the resultant of these 2. Is that okay?
Yeah,
Okay.
so kind of like broke it apart and made it 2 separate things.
Yep. And we basically took that one out of the picture and left with these 2. Because now these two that we've left on the picture, one's on the x-axis, one's on the y-axis. Okay? So, Monty, I was actually going to go there next. So this one here, we could label this as applied force, but it's not the applied force, it's just the y component of the applied force. Whereas this one here is not the applied force, it's the x component of the applied force. Does that make sense? Okay. So now, taking it back to Newton's second law, but only Newton's second law on the x-axis, we have two forces on the x-axis. We have the x component of the applied force plus the force of kinetic friction have to together equal mass times the acceleration along the x-axis. Good there? And if we go back and look, we should have everything in this equation except for the one thing that we're looking for. Alright? Do we have the applied force on the x-axis? Yeah. Yes. What number was it? Because I can't remember because it's all different. 77.9 newtons plus the frictional force, right?
Negative.
What was the number? I can't remember.
75.
75.6, but because it's in the opposite direction, we got to make it negative, right? And that equals the mass, which they gave us in the problem, 20 kilograms, and then that leaves us just with acceleration along the x-axis as our only unknown. And so we should end up with something pretty small, right? What is it?
0.115.
Technically we should, because the direction is in the positive direction on the x-axis. Yeah, technically we should. So, okay. And that's our acceleration along the x-axis. Good there? So, it is a long problem, but it does. So, to wrap it up,
Because you had to find normal force to get the
yeah, to use the coefficient, you got to find the normal force, and you can't just assume that the normal force is gravity in this case, because there's that other upwards component. So yeah, is it a long problem? Yeah, it's a long problem, but conceptually, we really didn't do anything new in this problem, right? We've done all these things before. We've broken forces up into components. We figured out the normal force from the other y component forces. These are all things we've done before. Okay? Good there? Let's do one more real quick. Okay? Not quite as involved as this one. And let's go here. All right. So here's a car. Okay? And it gives you two forces that are acting on this car. We are looking at this car from the top view. That might make a difference when we start going to do free body diagram. Okay? So two questions. It says, A, what is the resultant of these two forces? And then B, if the car has a mass of 3,200 kilograms, what acceleration does it have? So first, let's handle part A. If it says what is the resultant of these two forces, we have calculated the resultant of forces numerous times in here. Okay? We haven't called it this, but we've done it. We said the resultant represents the sum of two vector quantities. What name do we give to the sum of two forces? The net force, right? A is asking you in a it gives you a mass, what acceleration does it have? So B is asking you to solve for what? Acceleration. Can we make any assumption in this case about x-axis or y-axis like we could in the last problem? Not real easy to do in this case. So here, we'll just leave part B as acceleration. Okay. Good so far? No? Alright. So, first things first. The net force. Finding the resultant of these two forces. First, here they drew a y-axis in here as a dotted line, right? And then if we wanted to, we can put an x-axis in like that. Those two forces that they gave us, are they on the x-axis? No. Are they on the y-axis? So what are we going to do with them? Break them up into components, right? So we got a force that's acting like this, and then we have a force that's acting like this, right? If we go components, right, it gave us a couple of angles there, but that doesn't mean we necessarily have to use the angles that they gave us, right? For red, we know it has a vertical component and a horizontal component. And for blue, we know it has a vertical component and a horizontal component. But when we draw them that way, sometimes it gets a little crowded, especially on the y-axis there. Right? You can draw this picture, that's fine. But you can also draw this picture. It's exactly the same thing. Those are the two components, whether I go up and over first or whether I go over and up first. It really doesn't matter. Okay? The one thing that will change in this problem is that the angles that they've given us relate to the first triangles that I drew. I can fix that problem, though, just with a little bit of math, right? I know that x-axis, y-axis has to be 90, so if this angle is 30, what's the other angle for the other triangle?
60.
This has to be 60, right? And then that means this has to be 80. Okay? Good there? All right. So, first things first, components. Go.
I would do it if they know he is. Without a doubt. Yeah, no.
All right, good with those numbers so far?
But we skip Tuesday. I would do that later.
Yeah.
We don't wait until like it's half a year. Yeah, that like 2 weeks span.
Are you at 78.2? I had 78.14.
I had 78.14. Yeah, I did that as well. What I
All right, you got those? So, we've done this before. It's been a while, but we've done this. If we want to find the resultant, or the net force of these two, making use of a idea that we used in equilibrium, we're going to find the net force on the x-axis, and then we're going to find the net force on the y-axis. So breaking it up into the two axes, right? On the x-axis, how many forces? 2, right? So, Imani, just to kind of carry out from what we did before, right? We said that taking these forces and breaking it up into components is basically the equivalent of getting rid of all this and leaving us just with that, right? Okay? So, if we look on the x-axis, Bridget, how many forces? 2. What do you see about those 2 forces on the x-axis? Opposite direction, so what are you going to do with these 2? Subtract them. Did you do that already, Bridget, or not?
No.
Okay, so when we add up the x-axis forces, we end up with 111.9, and we'll call that in the positive direction, because generally that's the positive direction on xy axis in math, right? Then on the y-axis, how many forces on the y-axis in this problem? 2, right? What do you see about those 2? They point in the same direction, right? So, when we add those up, what do we end up with? 772.3. And we'll also call that in the positive direction. Right? But in this case, it's not asking us to balance the forces out. It's just asking us what's left over, right? So that's what we did like when we did equilibrium, right? But here it's just asking us what's the net force. Okay. All right, so then that left us with, where was it? Let's extend this down a little bit. That left us with 111, what is it? 0.9 in this direction, and then 772.3 in this direction. Okay? So here, we can't actually find the resultant the way those 2 are set up, right? We've got to make ourselves kind of like a triangle like this. This goes here, and that means this one is actually the net force. Alright?
Do you have to flip it like that?
No, you can actually do it the other way too. Okay? But, Bridget, the important part being that the x component and the y component, they have to be set up what we say tip to tail. So technically if you did this, you could kind of draw a arrow that looks like this, and you would get the same number.
It's not the same
It's not the same
direction.
direction though. Yeah, that's the problem. Alright? So yeah, when we set up our vectors, they have to be set up tip to tail. So you can set them up that way, or you can set them up horizontal first, then vertical. It really doesn't matter. Okay? Don't forget, once you find this hypotenuse, you're not done yet. You need an angle theta in there as well, because force is a vector quantity. It has magnitude and direction. Good with those 2 numbers? So, to answer the original question, the net force would be 780.4 newtons. That might not be the right sig digs, but that's okay. And then we would say 8.24 degrees. And we would probably say, I would probably describe it as right of the y-axis. Good there? Go ahead.
I used the tangent for that.
Yep.
Is that okay?
That might, we just might be using different rounding, like you might have put different numbers in. Yeah, that's fine. Yeah, that's, oh yeah, that's, yeah. So, well, if you use tangent, you should be using the hypotenuse.
Yeah, it's not because it's opposite.
Because tangent's opposite over adjacent, right?
Yeah. No, I said I didn't use that.
Oh, I didn't either. I didn't either. It might just be a rounding thing too, so. Yeah. Alright, good there? Then, to answer the last question, right? The last question says, what acceleration? Well, what did we just figure out? We just figured out net force, right? What else did they give us in the problem?
The mass.
They gave us the mass, right? So if we have net force and we have mass, we should be able to figure out acceleration. Right? So 780.4 equals 3,200 times A. The problem set that I gave to you today as you walked in the door deals with these concepts of not equilibrium in 2 dimensions. Answers are posted online. You can do a couple for practice either tonight or sometime before test. Tomorrow we start in on the inclined plane. Woo-hoo.